allows us to count the number of galaxies in the observable universe. The number of galaxies it's possible to see, that number is 2 trillion. So the piece of the universe we can see contains 2 trillion galaxies. The universe is 13.8 billion years old. I keep saying these numbers, how do we know? I want to spend just a few minutes in the second half of this talk talking about the science of cosmology and how we know these things. So how do we model these things? How do we make measurements? How do we make predictions about the future of the universe? How do we understand its past? Well, in some sense, but I'll correct myself in a few minutes, we can only see the present. Well, the way we do it in cosmology is to have a physical theory, a framework within which we can make sense of observations. And that framework is easy to identify. It's 100 years old. It was first published in 1915. It's Einstein's theory of general relativity. It began life, and that's what this diagram is a theory of gravity. So a theory with no ambition beyond, in some sense, Newton's law of gravity. It's a better theory of gravity than Newton's because it makes better predictions. It's a different model for what gravity is, and that's what I've drawn here. In Einstein's idea is this. So because of actually measurements going way back into the 1800s on electricity and magnetism and the nature of light, Einstein was led to suggest that space and time are not what we consider them usually to be in everyday life. So we tend to think of space as a box within which things happen, right? The universe, if you like. And we tend to think of time as something that ticks along, so something you can measure on your watch. And we tend to think of them both as being universal, in the sense there is one space, and if we all had perfect watches, then we synchronized them all, and then we went away and came back to this room next year and looked at our watches. If they were perfect, we would think they would still all read the same time. Time is absolute and universal as well. Einstein realized that observations throughout the 19th century was telling him this was not the case. I could give you a lecture course on this, but we'd be here for a month or 2 months. We probably will be. They probably won't let us out, will we, in isolation? If that happens, then I'll give you a full lecture course on relativity. The upshot, though, in Einstein's mind, was that space and time should be merged together as concepts into a single concept, which is called space-time, often called the fabric of the universe. And his great realization that led him to a theory of gravity was that fabric can bend, it can curve, it can stretch and shrink and warp in response to the stuff that is in the universe. And that's what I've drawn here. So I've drawn the planet Earth in the fabric of the universe, in space-time, and the presence of the Earth, the matter, the energy, the mass of the Earth is causing that fabric to distort. And then Einstein's picture of gravity is quite simple. If you imagine sending something in through this distorted fabric, rolling a little marble around on this picture, that would represent the moon in this case, then it would not travel in a straight line, because the fabric through which it is moving is distorted. You can sort of see, if you sent it in at the right way, that it might go round and round. It might go into orbit around the Earth because of the distortion of the fabric. And that is Einstein's theory of general relativity. You can quantify it, of course. You can make it mathematical, it makes predictions. It is a tremendously accurate theory of gravity, the best that we have. Just to demonstrate how good it is, I want to talk about a discovery that was made last year, which concerns probably the strangest objects in the universe, black holes. So black holes are at the frontier of theoretical physics. They are the collision of our ignorance, if you like, in many fields, both gravity, quantum mechanics, and so on. They raise profound questions about what our reality actually is. But Einstein's theory predicted their existence back in 1915. He didn't know that at the time. His theory predicted them much later. But the unchanged theory from the one he published in 1915 demands, essentially, that these things exist. Now, I want to show you a simulation using Einstein's theory of general relativity, and this was made for me, I made this with a graphics company about 18 months to 2 years ago now. So before we made an observation of what a black hole looks like, but this is the prediction from Einstein's theory. What you're seeing here is a camera flying towards a black hole, and it's going to go into orbit around the black hole. Now, immediately as we start approaching it, you see there's distortion in the star background. That distortion is calculated only using Einstein's equations. I should say the software that we used to do this was developed for the film Interstellar by a company called DNEG. When Chris Nolan, the director of Interstellar, wanted a black hole, which is a key character in the film, he didn't want an artist's impression. And so he essentially paid for the graphics company DNEG to code Einstein's theory of general relativity into the graphics software, and that's what we used to make this simulation. All there is in this simulation is the black hole described by two numbers, which is its mass and its spin, just two numbers, a flat star background, and a flat disk of material like Saturn's rings that we put around the equator of the black hole. So that is the only artistic input, if you like, into this simulation is the disk of material around it, but it's completely flat. And then when you turn on the general relativity and make the simulation, the flat disk around the equator of the black hole is heavily distorted from our viewpoint because of the curvature of the fabric of the universe. So what you're seeing there, in fact, if you look above the black hole, you're seeing in fact, above you're seeing the front side of the disk all the way around, the top half of the disk. Behind the black hole as well, distorted upwards around the top of the black hole, and underneath you're seeing the underside of the disk, the whole thing distorted around. So you see, when you look at a black hole with a disk of material around it, which is what we think happens in black holes, stuff spiraling in, you see the whole disk, and you see the whole black hole actually. So all 360 degrees of the black hole you see because of the distortion of the paths of light. So there's all sorts of distortions. We could give a whole lecture course on this. But what I want you to focus on is two things. One is it is a simulation using a 100-year-old theory of gravity, curvature of space-time. And secondly, look at the shape of the black hole, which is a prediction of what we think a real black hole will look like. Now, 1 year after I commissioned this graphic and we made this graphic, a photograph of a black hole was acquired. It was acquired by a collaboration called the Event Horizon Collaboration. And what they did was they linked radio telescopes up around the world, both northern, southern hemisphere, east and west again, Asia, North America, Europe, and actually even this one, which is one of the most exotic telescopes in the world, at the South Pole. So this is a South Pole telescope. When you do that, you build a telescope that is effectively the diameter of the Earth. And so it has tremendous resolving power. It's incredibly difficult to do because you've got to know that all the light's coming from the thing you're looking at, you've got to synchronize it. It's a massive engineering challenge, but they managed to do it. And what they did was they pointed this Earth-sized array of telescopes into a galaxy, which is called Messier 87. And if I get my little laser pointer, it's this big one. So if you can't see, it's the one in the middle of this image. This there, all the way over there, that one. This image, by the way, is an image of the sky in the constellation of Virgo. It's called the Virgo supercluster of galaxies. And in fact, even if you have a small telescope, even perhaps not in London, but if you go out into somewhere dark and you look into Virgo, you see these galaxies. It's like galaxy soup, hundreds of galaxies in this region of sky. And this is a beautiful photograph of that. You see all those galaxies. But the big one in the middle, Messier 87, it's a big galaxy, about 1 trillion stars, 55 million light years away. And we had strong evidence that there was a black hole at the centre of this galaxy. And so what the Event Horizon Collaboration did was focus the Earth-sized telescope into the heart of that galaxy, 55 million light years away, and took this image, which you may have seen actually, a very famous image. This is the first photograph, actually from radio telescopes, but it really is a photograph of a black hole at the centre of a galaxy. And the most remarkable thing is it looks like the black hole in the simulation. It didn't have to. Some of the characteristics, which are very odd actually, so the black circle in the middle, you might call it the event horizon. It's actually called the shadow of the black hole. It's the region from which no light can escape and nothing can be seen behind it in the star background. That didn't need to be there. It tells you there is such a thing. But also the shape of the material, which will be in a disk and will be spiraling into the black hole, but the distortion of the picture, the image of that disk as seen from Earth 55 million light years away, is heavily distorted, as predicted by Einstein's theory. I gave a talk actually somewhere where there was a slightly more cynical audience, and someone said, it's a bit blurry, isn't it? I said, like, oh, fuck off, it's 55 million light years away. It's actually remarkable. I mean, by the way, this is a big, well, how big is it? What's the scale of this thing? So it's, the black hole is about 6 billion times the mass of the sun. So it's what's called a supermassive black hole, 6 billion times the mass of the sun. And the radius of that shadow, the event horizon if you like, is about twice to 3 times the diameter of our solar system. So it's a big structure, it's a solar system sized structure. But remember, it is 55 million light years away. So it's a tremendous technical achievement to take a photograph like this. But the key thing is, it looks like the prediction, which is a straightforward prediction of Einstein's 100-year-old theory. So it's passing every 21st century challenge that we throw at it. And there's a lot of information in here. And again, I could talk forever about the information in there. But I want in the last 10 minutes or so to bring these ideas together. So I've talked about the size and scale of the universe. And I've talked a bit about the framework that we use to describe the large-scale evolution of the universe. How does this theory of gravity, which is a good theory of gravity, translate or become a theory of cosmology, which is a theory of the origin and evolution of the universe? Well, it became a theory of cosmology actually before the idea of black holes was extracted from the theory. In the hands of just a few physicists. And in some sense, it had to be the case. We're talking about 1918, 1920. There weren't actually that many physicists at the time. But there are 2 that really stand out. It's unusual actually in science. I mean, quite often science is done, and certainly today, by big groups of men and women across the world. Back then, as I said, there weren't that many physicists. But also in this case, there were only 1 or 2 that were taking Einstein's theory and doing something very bold with it, which was applying the theory to the universe as a whole. How can you do that? It occurred to Einstein pretty quickly. It's easy to say in words what occurred to him, but it's a bold idea. The idea is this. So I showed you earlier that picture of the Earth, with the fabric of the universe being curved by the presence of the Earth. And that's the way that we did the black hole simulation, by the way. You put the black hole into the theory, it tells you how the fabric of the universe curves, and then you can trace the light rays around through that curved space-time, and you get the images that we saw of the black hole. So what you do in the theory, if you want to calculate that, which is what was done in that simulation, is you put, well, in the case of a planet, or let's say a star, you put a spherical distribution of matter into the equations, essentially, which is the star, and out comes the shape of the fabric of the universe in the vicinity of that star. So it's like a little machine, Einstein's equations. In goes the matter distribution, out comes the shape of space and time, and you can trace light rays through it, or put something in orbit around it, and so on. What Einstein thought in about 1917, so in a couple of years after he published the theory of gravity, was that, well, if I can do that for a solar system, for a star like the sun, as we calculate the orbits of planets, why can't I do it for the universe? Which is an easy thing to say, but a bold idea. But the idea is quite simple. The idea is, if you knew the matter distribution of the universe, then you could surely plug it into the equations, and out would come the shape of the universe in space and time, which is in fact the past, present and future of the universe. So the whole history of the universe should, if you know the matter distribution at some point, come out of the equations in the same way that the history of the solar system comes out when you know the matter distribution of the star, which is a sphere like the sun. Now, you could argue 1917, we didn't know the matter distribution of the universe. We didn't even know, actually, at the time, there were galaxies beyond the Milky Way galaxy. But what Einstein did is, what, and again, if there are scientists or people who did science at university in the audience, you'll know this. What you do is you try the simplest thing. That's the rule. That's how you do science. You make the simplest possible assumption and you try it. And you see what the consequences are, you work it out in the theory, and if you get something that doesn't agree with what you observe, you throw it away and do something more complicated. The simplest possible assumption you can make about the matter distribution in the universe, on average, as a whole, is that it's uniform. right? That it's everywhere is the same. It's the ultimate Copernican principle, if you like. So you just assume that on the average, on very large scales, those galaxies are just scattered randomly across the universe, which is a pretty good approximation we now know. Einstein didn't know that, but he did it, so he took a uniform matter distribution. When you do that, you can solve the equations. And the equations tell you what happens to the universe. They do tell you the history of the universe. What you get is, I've drawn it here, a very simple thing. You get simple in, uniform matter distribution, simple out. I've drawn here 3 galaxies in the fabric of the universe. So whilst the space-time is very curvy and warped near the galaxies, these are very small little things. They're almost like bits of dust on the large scale of the universe, as we saw earlier. So broadly speaking, the theory says uniform matter distribution in, smooth space and time out. So I've drawn it here, just this very smooth grid of space and time. Fine, except that things are much more interesting than that. Because what always happens in the theory is that the universe does not stay like that. The fabric of the universe does do something in response to all that matter and energy you've scattered throughout it. What it does is it tends to stretch or shrink, depending on how much stuff you put in. So in other words, the theory demands that the universe is dynamic. It changes all the time. And in general, what tends to happen is that into the future, things tend to stretch, and into the past, things tend to shrink. So I've drawn the galaxies here, all in the same place, but essentially you go down the slide, you're going back in time, and the galaxies are getting closer together. Now, Einstein did not like this at all. He hated this behaviour initially, because Einstein had a philosophical predisposition for an eternal universe. He thought nature should have existed forever, it should be eternal, unchanging, infinite into the past, infinite into the future. His theory was not suggesting that. And in fact, he spent quite some time messing around, adding extra bits to the theory to try to counteract or prevent this behaviour. And this is where the other photograph comes in, Georges Lemaitre. Lemaitre was a physicist, cosmologist, working at the same time independently as Einstein, made the same assumptions independently and got the same results. He did the same mathematics. But Lemaitre is important because he saw something different. Same behaviour, very different conclusion. Lemaitre thought this is correct. Why? Because he had a different philosophical prejudice. And you might be able to see why, actually, in this photograph, because Lemaitre was a priest as well as a physicist and a mathematician. And he was once asked beautifully, very famously, how can you be a priest and a mathematician at the same time and a cosmologist? And he said, there are 2 roads to the truth and I choose to take them both. I thought it was a nice thing to say. So what Lemaitre saw here was a universe, a theory that's telling us the universe, the distances between the galaxies tends to shrink as you go into the past, because the fabric of the universe is stretching as you go into the future. If you think that's true, then it looks like there must be a time in the distant past when all the galaxies are very close together, or essentially on top of each other. And Lemaitre started talking, giving lectures, talking about the theory suggesting there was, in his words, a day without a yesterday. A day without a yesterday. It's a beautifully poetic man, Lemaitre. What he's referring to is what we now call the Big Bang, which is the time in the past which you can calculate from this theory. If you know where the galaxies are today and how fast they're receding from each other, then you can plug that into the theory and run time back and find out where the day without a yesterday was. And that's what we do, essentially, today. So we calculate the age of the universe from observations today of how fast all the galaxies are receding from each other. Lemaitre didn't know that at the time, but the theory is suggesting that that would be the case. And Einstein, actually, they met at a conference in Belgium in the mid-1920s, and Einstein said to him, your mathematics is excellent, but your physical intuition is lousy, because Einstein disagreed. Ultimately, Einstein had to agree because Edwin Hubble, in the late 20s, proved or observed that the galaxies are indeed receding from each other. But it's a remarkable thing that it's almost true to say, it's not quite, but almost, it's a strong suggestion of the theory. It's almost a prediction of Einstein's theory that that would be the case. A theory that was developed as a theory of gravity and space-time is strongly suggesting and giving us a framework to understand that the universe had an origin way back at the Big Bang. Now, of course, you have to make observations. This is a theoretical prediction of a theory of gravity we're applying to the entire universe. There are plenty of places we can go wrong there. I want to finish by showing you and just discussing for a few minutes the best piece of evidence we have today, and the one that has the most information content telling us about the early universe, that this is the correct picture, that indeed there was a day without a yesterday. The way we do that is, if you think about, I spoke earlier about the Andromeda galaxy, and I said that it was 2 million light years away. If you think about what that means, it means the light has been travelling for 2 million years to get from the galaxy to your eye, or your binoculars, or the camera. So you see the galaxy as it was 2 million years in the past. So you might ask the question, well, if that's true, then can I look far enough out into space that I see light that's coming not from things that are 2 million, 3 million, 10 million, a billion light years away, but light that has travelled 13.8 billion years across the universe? In other words, can I see the imprint on the sky today of the day without a yesterday? Because I can look far enough away. There's a beautiful quote from Lemaitre, actually. So he's a poetic man. He was asked later in life, what did you think? You know, when you saw this theory, which is strongly suggesting that your philosophical or maybe theological prejudice is correct. There is, because you think what a day without a yesterday is, in Lemaitre's terms, it's a moment of creation. It's I suppose the biblical account of creation, as he would have said it, is being shown to be true by the theory. And Lemaitre said this. He said, so he was asked to picture that moment and picture how he sees the universe today. What a remarkable thing it is that we've been able to understand that standing on our planet. And he said, standing on a well-cooled cinder, we see the slow fading of the suns and try to recall the vanished brilliance of the origin of the worlds. The vanished brilliance of the origin. That's what we do because it lands on the earth. The vanished brilliance of the origin of the worlds, well, we can see that. We have a photograph of it today. This is a photograph of the vanished brilliance of the origin of the worlds. It's taken by a satellite called Planck, a European satellite, and it's known as the cosmic microwave background radiation. This is a photograph of the oldest light in the universe, that light that's journeyed across the universe for 13.8 billion years. It's presented like a sphere because we have a photograph of the whole sky. So this is as far as you can see, if you like, in every direction. So it's a picture of the celestial sphere, if you like, but as far as you can possibly look. What you're looking at here is an almost uniform glow. The colours correspond to very slightly different temperatures in the sky, which correspond to very slightly different densities in an almost uniform mass of gas. All there is here is hydrogen and helium, and the differences, which were first detected in the 1980s, are at 1 part in 100,000. That is all. So we have a photograph of the universe before there were stars and before there were galaxies. It's a glowing mass of the two simplest chemical elements, hydrogen and helium, almost completely uniform. So this is a photograph as far back as you can look. It's in fact about 380,000 years after the Big Bang, quite accurately, 380,000 years. We know that number because before this time the universe was so hot that atoms couldn't form, and so the universe was in what's called a plasma state, and light can't travel through that universe. So the universe is opaque if you try to look further back than that. But as you go through, as the universe expands and cools, at this moment, then the atoms, it was cool enough for atoms of hydrogen and helium to form, then the universe becomes transparent, almost in an instant. And the light from that time can travel across the universe from then on, and that's the light that we see here. So this is a photograph of the universe 380,000 years after the Big Bang. And the key point is it's very hot, very uniform, there are no stars and there are no galaxies. So this tells us, it's a photograph that tells us that Einstein's theory is correct in this sense. The universe was once very different to the universe we see today, and it's changed. By the way, these colours, these slightly overdense regions, are extremely important because without them we wouldn't exist. Because what we know is as the universe expanded and cooled from this point, the regions that were slightly denser would have, just their gravity would have ultimately caused them to collapse into the stars and galaxies. And remarkably, very remarkably, the pattern that we see in this photograph is, or can be mapped onto, if you like, the pattern we see in the galaxies. So the answer to the question, why are the galaxies distributed in patterns across the sky today, as we see them, is because they replicate or they grew around the pattern that we see in this most ancient light in the universe, and we understand that process. Now, just again, I give you whole lectures on these things, very, very briefly, because I've come to the end. Where did that pattern come from? It's an extremely good question, because this is actually George Smoot, the physicist who got the Nobel Prize for first seeing these slight variations in the distribution of gas in the early universe, called this picture the face of God. He said it's like looking at the face of God. He was not a religious man, but what he meant, what I said earlier, was that without these patterns, without these tiny ripples in the gas in the early universe, there would be no stars and no galaxies and no animals and living things and people and so on. Where did they come from? Well, remarkably, we have a theory called inflation, which is a theory of what happened before the Big Bang, by which I mean what happened before the universe became hot and dense in the first place, 13.8 billion years ago. We now strongly suspect the universe was around before that time, but it was cold and it was empty and it was accelerating very, very quickly in an accelerating fast expansion, which is why it's called inflation. And then we think that that phase in the universe came to an end, and all the energy that was driving that expansion got sort of dumped into space, heated it up, and ultimately that's the energy out of which we and everything we see in the universe today is made. And that's what we call the Big Bang, the end of inflation. And incredibly, our theories of the physics that we have now, our theories of nature, seem to be applicable during that early phase in the history of the universe. And what we can do is we can calculate we can take a patch of space that's about less than a billionth of the size of the nucleus of an atom. And we can expand that using Einstein's theory all the way up to when the very fast expansion stopped and everything collapsed and heated up, and then carry on expanding it to the universe we see today with 2 trillion galaxies in it. When it was a billionth of the size of the nucleus of an atom, we can calculate how ripples, using the theory of quantum mechanics, would have got imprinted into the universe at that time. And those calculations match this observation, and those calculations were made before this observation was made. And they also match the distribution of galaxies on the sky. So we can claim, with some justification, that we can at least speak of the universe evolving, the universe that we see with 2 trillion galaxies, from a patch of space-time that was less than a billionth of the size of the nucleus of a single atom. And we have a consistent picture, and we get it pretty much right. Now that's textbook cosmology. It's not to say that's the correct description, but it's the best description we have of why we are here. So, I suppose to summarise, there's a lot of information there, but I think for me, one of the great paradoxes that cosmology raises, as I said at the beginning, is this paradox that these vast expanses of time, vast expanses of space, trillions of galaxies in the universe, obviously mean that in a very real sense, this planet doesn't matter very much. However, it is potentially, as I underlined, the only place in our galaxy, so the only place in the local neighbourhood, and by neighbourhood I'm defining several million light years, where atoms have come together from those earliest times. Hydrogen and helium atoms have managed to come together to build structures that can understand atoms, and that can build a theory that can tell us potentially how, not necessarily how our universe began, but how our universe evolved from a time possibly even before the Big Bang. And that's a remarkable thing, and I think honestly that's the best description that I can give of our position in the universe. So cosmically significant, no, but locally significant, in a few million light years, quite possibly yes. Thank you very much.